Welcome back.
7.1.
7.1, yes.
What page?
We are on page 9, yes. So just as a little refresher, since it's been so long, and I know I told some of you this, but we only have to finish 7.1 and then do 7.2, and then that's it. I looked at 7.3, and I was like, I don't think that's tested on the AP exam, and I checked into it, it's not. So we're going to do 7.2, and we're donezo. Reviewing from here on out. So that's good news. So we'll probably do like another quiz for chapter 7, and then like a chapter 6 and 7 like test, and then we'll review.
Can we go over chapter 6 too then?
We'll review over chapter 6, yeah, don't worry. But first, let's finish chapter 7. So we've been looking at the area between two curves, and then we started looking at examples like this, where it would have made more sense to use like the horizontal strips, or like the horizontal rectangles, as I like to call them, and to figure out like the height of each. We do like the right minus left instead of like the top minus bottom. So this is what we usually do. Let me go back to one with respect to x quick. A picture like this where we take the vertical strips, and the width we always call dx, and then the height of the rectangles is the top of the curve minus the bottom. Top minus bottom is what you need to know. So then we looked at just, I think, a couple examples of doing it with respect to y. Okay, so this one's similar, and usually like if your equations are written this way, where they're in terms of y instead of in terms of x, that's usually like an indication that, okay, this is probably going to be something where we're going to do this with respect to y, okay? Now, the tricky thing is you're not used to graphing something like this, and your graphing calculator can only graph in terms of x. Like there's no like setting to change it to graph something like this, and you can't just use the variable x, obviously, because that's different. So what you have to do to graph these is you basically just have to solve these like for y, and then you can visualize the graph a little bit here. Okay, so g of y, just like you know how f of x is the same thing as y. Well, same notation here. If you have g of y, that's really just the same thing as x. So this is the same as x equals 3 minus y squared. So I'm going to solve this for y just so it's easier for me to graph. Okay, so I'm going to go ahead and add over the y squared and subtract the x. Square root both sides, don't forget plus or minus. All right, so now this is a square root curve. Couple transformations here. This is reflected, and it's shifted to the right 3. So it's going to look something like this. Or again, you could plug in like a couple points, or if you have your graphing calculator available for you, you could graph this to get a better visual. So this is shifted to the right 3. And this negative on the x reflects it over the y-axis. So instead of going off in this direction, like our normal square root curves, it goes off in this direction. So here's the plus, here's the minus. That's that curve. Again, that negative would reflect it then over the x-axis. Okay, and then this one right here, nice and easy to solve for y. I'm like, okay, this is a nice linear function with a y-intercept of -1 and a slope of +1. So up 1 over 1, up 1 over 1. Does it intersect there? We probably don't know that for sure, but actually we do. Bless you. Does that sneeze?
Yeah.
Bless you. Okay, so depending on how accurate your graph is, so I was kind of just like asking myself, I was like, is this exactly where it intersects? Or like down here, we don't really know for sure. But just to make sure, because I didn't really sketch any other point on my square root curve other than this like key point right here, and then I kind of just sketched it to the left. So just to be sure to check for the point of intersections, we should set these equal to each other. And you can set the original equations equal to each other too if you want, like the 3 minus y squared. When is that the same as? So again, as a review, this is to find the intersections. And some people do this like first before they graph them too. I kind of like to, if I know how to graph it, especially if it's a nice, easy like parent function where I know quite a few points, I can usually figure out what the intersections are graphically, but it's always good to check it algebraically. So y plus 1. So here we can get the y coordinates of 1. They're the same. Okay, so I'm going to move everything, set this equal to 0. So we got y squared plus y minus 2, which would factor into y plus 2, y minus 1. So these should intersect when y, careful, we're solving for the y coordinates, when y is negative 2 and when y is 1. Okay, so that one I marked on my graph there when I was graphing my slope. That makes sense. That's when y is 1. And then when y is negative 2 is this intersection point over here. And because we're doing this with respect to y, we want to know the y coordinates of where they intersect, because that's going to help me with my bounds. Okay, so we need to mark that. So what I'm trying to find is this area right here. Okay, so then you have to decide, and like I said, this one there's a little bit of a hint that we're probably going to do this with respect to y, because my equations were in terms of y, but here's where you have to decide, am I going to use vertical strips or horizontal strips? And if you notice, if you were to draw in vertical strips here, you're like, here the red curve would be the top and the bottom, so I wouldn't be able to like define the height of that rectangle. But anytime I draw a horizontal rectangle in, or like a horizontal strip, and honestly, folks, too, you could just like literally like flip your paper like this, and we're doing the same thing. We're doing the top minus the bottom, which is the right minus the left, right? If you look at it this way, okay, to find the height of that rectangle, I can draw a bunch of vertical strips. I would take the red minus the blue. So that's really the same thing we're doing, just with respect to y. Which means when I say with respect to y, that means in your integrals, everything has to be in terms of y. So y's only. So to find this area, I would integrate. Okay, we're doing this in terms of y. So from negative 2 to 1, from negative 2 to 1, the lowest to the highest, we're doing the right minus the left. That's going to give me the height of the rectangles. And then we're going to times this by dy. That's technically the width of the rectangles. And then this integral will let me sum up the area of all those rectangles. Okay, so my right curve is the red one. In terms of y is 3 minus y squared. Again, the only reason we did this was to help us graph it. Right minus left in terms of y was y plus 1. And then we're going to go ahead and multiply in dy. Okay, that'd be how you'd set up that area. Then from there, it's just a little algebra, a little bit of calculus. So let's just go ahead and simplify this a little bit. I just rewrote it kind of like in standard form here. Negative y squared minus y plus 2 dy. Antiderivative refresher. Add 1, divide by that new power, so that'd be negative 1/3 y cubed minus 1/2 y squared plus 2y, fundamental theorem of calculus, plug in the upper bound, minus plug in the lower bound. All right, I got 9/2, or 4.5, however you want to think of it. You don't need units on these, just numerical values, because the only time you need units is when it's in a contextual problem, which that's what we're going to look at the second half of this lesson. Okay, remember this? Yeah, good times. All right, now we're going to do one problem where we're going to find the same area. We're going to do it one way with respect to x and one way with respect to y, just so you can kind of like see the difference. So it says, find the area of the bottom region bounded by these curves in the first quadrant, A, with using vertical strips. So that means with respect to x. And we'll visualize this in a second after we graph it. With horizontal strips, so with respect to y. Right now, the problem's set up for me to do this with respect to x because all my equations are solved for y, which is nice because it'll help us graph it. Okay, so I'm gonna start by sketching it, like I always do with these ones. So let's start with part A over here. And obviously, if we do this correctly, we should get the same area. Okay, so it says only in the first quadrant. So I'm just gonna section off that piece of my graph. We have the line y equals x, y equals 1, and y equals x squared divided by 4. Okay, I think I'm actually gonna start with this one. This is a parabola that has a vertical shrink by a 4. So it's going to be pretty like wide. So let's maybe just plug in a couple points. So when I plug in 1, I'm going to get out 1/4. Just going to do this for now. When I plug in 2, I get out 1. All right, so something like that. Just a pretty wide parabola. This is 1. Oh no, that was a 4. So let's say 1's about there. Okay. And then the line y equals 1.
Wait,
There's that one.
my x is 2.
Yeah. It'd be 1. Oh shoot, you're right. Why did I think it was 2? Why am I getting a phone call? From Lancaster. What if it's about my wedding ring that I dropped off? Just kidding. Okay, hold on. Let me do this better.
You said 1.
Did I say 1?
Yeah.
Okay.
I think you just labeled the graph.
I think I labeled it 1 and then I was like, oh, this is 1, but I was thinking on the x-axis 1. So let's call this 1 when I plugged in 2. Okay, so let's do this. Then 2 is 1. And then 1 is like a 4th of that. So something like that. Okay, thank you. Good catch. Okay, then y equals 1. I'll just be this horizontal line. You can draw arrows if you want, but they just told us quadrant 1, so I'm just sectioning off. And then the line y equals x. Okay, so that goes through the origin. It has a slope of 1, so 1, 1. Hiccup or?
That was a hiccup.
That was hiccup. Okay.
It's just not my day.
It's okay. We don't care. All right, so it says find the area of the bottom region bounded by these curves. So that would be this right here in quadrant 1. Orange. Okay. So they want us to use vertical strips. I'm thinking top minus bottom, but I have an issue here because if I look from 0 to 1, my top curve is always the blue, my bottom curve is always the green, but then when I look from 1 to 2, my top curve switches. So we need 2 intervals. Yep, remember that? So I'm going to section this off. So you can draw 1 vertical strip in here if you want, 1 vertical rectangle to visualize. Okay, I need to do top minus bottom to find that height. And then for my second interval, I'm going to have to switch what one I call my top. Okay, so my first one, we're doing this in with respect to x. This would go from 0 to 1. Top is x minus bottom is 1. No, sorry. Bottom is the green one. Bottom is x squared 1/4. I'm gonna write that as 1/4. X squared. Sorry, I think I was looking at the red rectangle. Bottom is green for all of it. 1/4 x squared. Okay. So there's this chunk. That's this chunk right here. From 0 to 1, where my top is the blue, my bottom is the green. And then, as I said, it flips in here. So we're going to have to add on. Remember, area is additive. So this is like one of our kind of like properties. From 1 to 2 of top, which is 1, minus bottom, which is 1/4 x squared. Normally, I kind of wrap my different functions in parentheses, but since they are all singular term, we don't really need to do that. Okay. Quick, let's do these antiderivatives, and I'll just tell you the answer here. So antiderivative x, 1/2 x squared. Okay, add 1 is x cubed, divide by that, so 1/12 x cubed. These ones, I would plug in 1 and 0, plus this one over here, antiderivative of 1 is x, minus, and then that 1/12 x cubed again. Here we plug in 2 and 1. Okay, we get out 5/6. As another reminder, you can easily check these in your graphing calculator. Now, unfortunately, when you have to do two separate integrals, you have to type that in your calculator as well. Like your calculator has no way of differentiating where your top and bottom switches. Like you have to manually type that in with your y1 and y2 if you have them already graphed. Okay, so there's using vertical strips. Not bad, but a little annoying because we had to do two separate integrals. Let's do it horizontally. Okay. So it's obviously going to be the same picture here. I'm just going to do a little quick sketch. Okay, same area, but this time we want our rectangles to be horizontal strips. So looking at this entire region and or like rotating your paper to visualize this as top minus bottom, or just looking at this right minus left, my right and my left never switch. So I just can find this area by just setting up one integral. So the only thing that maybe will be a little bit annoying for this strategy was my equations are in terms of x, and we're going to have to put them in terms of y.
Treat Lord, Gene Thompson, Daniel Waters, and Braden Richardson. Please report to the conference room. Gavin Gleason, Treat Lord, Gene Thompson, Daniel Waters, and Braden Richardson. Thank you.
Okay, so this one I would go from 0 to 1, because now I'm kind of looking at my y-axis here. So I go from 0 to 1, and I'm going to do my right minus my left. So my green curve, which is y equals x squared divided by 4, or 1/4 x squared, however you want to think of it. That's obviously right now in terms of x. So if I want to do this with respect to y, because I'm going to have the dy, that's what represents this with the change in y, dy. I have to get this in terms of y. So I just have to solve it for x. This isn't too bad. Just times both sides by 4. Square root both sides. Okay, so I have plus or minus, but because we're only using this one in the first quadrant, I'll leave you the positive one. So you can ignore this one. And then I probably would just simplify this a little bit and just write it as positive 2 root y. And even I would take it a step further when I go to write in my integral. I'm going to do 2y to the 1/2 because then I can apply my power a little easier. 2y to the 1/2. Okay, so when we're doing with respect to y, it's right minus left. So then my left curve is y equals x. Okay, no problem. So instead of plugging in x, we're just going to plug in y. Okay. Add 1 to the power is 3/2. Divide by 3/2 will give me 4/3. Minus 1/2 y squared. Plugging in 1, plugging in 0. You also get 5/6 for that. Which obviously makes sense because we were finding the same area, 2 different methods. Okay. I have a few more area ones to try. And especially I want to look at one where like you have to use your graphing calculator because there are some like that come up on the AP exam, like on FRQs, where your graphing calculator is required and you have to like store values and all that good stuff. So look at one of those. But that's pretty much the big idea for this lesson. Is finding the area of those two curves and just knowing sometimes one way might be more appropriate than the other. I'd probably do it this way with respect to y on this one. I don't know, maybe not. Okay. So let's take a look at this one, just like a little bit harder example. Find the area of the region bounded by these 3 curves. Okay. Let's pretend we don't have our graphing calculator to graph these. Just for practice. Ooh. All right, I'm probably going to start off with my parabolas here. So this one's easy to graph. That's a happy face parabola, shifted down 4. So there's your vertex. And then, from there, think of like your parent function for a parabola, 0, 0, 1, 1, 2, 4. Those all just get shifted down 4. So now you have the point 1, -3, -1, -3, and then 2, 4. If that's shifted down 4, that's going to be 2, 0, -2, 0. Really, like the more accurate or the more points you can put on your sketch, the easier it is once you go to find like your bounds or your points of intersection of the area regions. You do this in algebra too. You like graph and find areas of, well, you don't really find area, but you look at like shaded regions between curves and stuff. Okay, let's do this parabola. Let's tackle this parabola. Couple ways you could graph this. You could just plug in points if you wanted to. What you were probably taught, what I'm guessing you were taught, is to like put this into vertex form by completing the square. So like you would factor out like the negative. We just kind of went over this actually when we were doing some of those integrals. We had to complete the square. And you would take, you take half of this middle term, so half of 2 is 1, squared is 1. So we'd add in a 1. And then we would counter it. Uh-oh, I think I did this wrong. We would counter that, so we really subtracted a 1 by adding a 1 out here. So then this factors into x plus 1 squared plus 1. And that gives you an idea that the vertex here would be at -1, 1. And I know it's a sad face parabola. So no stretches or shrinks or anything. So 2, -4. It's going to cross here. Maybe do one more point here. -4. The nice thing about graphing parabolas is that they're so symmetrical that if you can find one point to the left, you get like 2 for the price of 1. You can find the other point to the right. So how I graph that from there, guys, and again, you can either like plug in points. Obviously, it's going to have a point here, 0, 0, so its mirror point over here to be at -2, 0. Or just like know your shapes of parabolas. Like I said, the parent function, 0, 0, 1, 1, 2, 4. And if there's no stretches or shrinks or anything, this really just got reflected. I mean, and there's my new vertex. But you can also plug in points once you put it into vertex form. Obviously, you have a reflection here, shift left, shift up. Okay, how are we going to think of it? And then we have x equals -3. That's just a vertical line here. Okay, so it's obviously going to cross this at some point, and you actually don't need to figure out when. You can if you want to. Do we need to figure out when? No, we're doing this with respect to x, so we shouldn't. All right, so this is a good example of, hey, I have 2 separate areas here. I have this one. I have this one. And again, if you guys were not sure where these cross, or if you're not sure how to graph these by hand, you can set them equal to each other and find their intersection points, and that might help you visualize it a little bit better. But the reason why, if you're looking at the purple region right here, the reason why I don't really need to know exactly where these intersect is because I'm going to do this with respect to x. I'm going to draw vertical rectangles. And I'm going from -3 to this point right here, which is -2. So it doesn't really matter exactly when these cross because I can see that no matter when I draw my vertical rectangle, my top is red and my green is bottom. So it's not like we're doing this with respect to y where I have to know what that top bound is, if that makes sense. Okay. So we have from -3 to -2. This one's the purple region of top, which is the red, minus the bottom, which is the green. With respect to x. Plus the orange would be from -2 to 1. Move this over a little bit. And in this case, my top is the green minus the bottom is my red. Okay. Are we good with like practicing anti-arrows and stuff? You kind of just want to tell you what the answer is. I feel like we've done enough of these. 38/3. Obviously, the new part for us is like setting these up from there. It's all calculus skills that we know how to do. Okay. So, not too bad because it was a nice, easy top minus bottom for both of those vertical strips, but 2 separate areas where the top and bottom are different. I like that one. Okay, here's the one where we need our graphers. So this one's like pretty, I feel like, important to follow along with on like your grapher too, because these are types of problems that you often have to do on the AP exam. So it's just a lot of good like calculator techniques. Find the area of the region enclosed by y equals negative x cubed and x equals 2y squared minus 3. So I have two different curves. One's in terms of x, this one, and this one's in terms of y. So this one's a cubic function that got reflected. So this is what cubics look like. So if it got reflected, it just looks something like that. Okay, not too bad. This one, if I want to graph this, I'm going to have to solve it for y. Right now, I don't know what this looks like. I'm guessing it's probably a square root curve. Looking at my setup here, how the y value is being squared. So let's go ahead and solve this for y. So add over the 3, divide by the 2. Y is plus or minus the square root of x plus 3 over 2. I don't have to rationalize or anything like that, but that's probably not something you know how to graph by transformations. You could make a table. You guys could find the key point, set this equal to 0. Okay, it's just going to be a fraction. That's okay. So if you were expected to graph something like this, you would have your graphing calculator, and especially you'll see that like intersection points, like these bounds, are not exact values. Okay, so when that happens, you would definitely get your calculator to do that. So let's go ahead and go to our y1 and y2. Clear out whatever you got in there. Okay, so y1, I'm going to do my cubic. I'm going to see if I can change my color because I want this one to be red. I'm going to change it to blue because this one I put my blue ink. Wow, look at all these color options.
Why did you just put like the first one down below?
Because I want to keep it in like the same order. Like negative x squared is listed. I don't know. You know, I just how to be difficult. Okay. So this one we're gonna actually have to type in two different lines. You can make them both blue if you want to. So we have the square root of, in parentheses, x plus 3 being divided by 2. And I would just type it in just like that. It's all underneath the radical. I know it feels uncomfortable having fractions under the radical, but you don't have to do the algebra here. I'm going to change this one to blue too. Whoa, we'll end with this problem. We're almost done already. Gosh, time flies and you're having fun, huh? Okay, so then we have to do the negative version of this, or the reflected piece of this. So negative, forgot my parenthesis, let me add that in. Okay. I think my window is just at that huge negative 10 to 10. We can zoom in a little bit here. Let's maybe go negative 5 to 5, negative 5 to 5, just to get this a little smaller scale and zoom in a little bit. Okay. So we're trying to find this area, this region. So by looking at this, do you guys think this is a better setup to do with vertical rectangles or horizontal strips of rectangles? Horizontal, good, because it never switches, right? If I were to draw in a horizontal strip here, it's always going to give me like that right minus left setup. If I would have done vertical, looking here, your top minus your bottom are those two blue curves. So we definitely want to do this with respect to y. Okay, so to set up our integral, we need to figure out these intersection points right here. I need to figure out when it intersects here. That's orange. And here. All right, so we're going to hit second calc when these intersect. All right, first curve, it's on my cubic. Second curve, I want to go down to the bottom half one. Okay, so it's a pretty long y value. It's this negative 1.43673. All right, so what we're going to do is you're going to go second. You're going to quit out of your graphing for a second. Here's remember how to store values on graphing calculators. If you hit alpha y, it will feed down that y value from that intersection point. Alpha y. So what we're going to do is we're going to store that. So you're going to hit the STO. We're going to store that as, and you can pick any letter. I'm just going to use B. Store that as B. So now it has that number stored as B.
How'd you get y up there?
You just hit alpha y and then hit enter. And it should feed in that y value of the intersection point we found.
Wait, where's y?
Right above 1.
Where'd you get this story?
Right next to 1. STO arrow. Is there something else?
I can get negative one, but I think I can put any.
You keep getting 1.
Yeah.
You're getting the top intersection point then. Did you get it?
How'd you get those?
I see.
Same. How did I? Oh, I hit store alpha B. I just picked B because it's my lower bound. You can use A if you want. It doesn't matter. Just don't use X or Y. Did you get it, Delaney?
Yeah.
Okay.
Well, I didn't think about equation. Right.
So now if you enter in B, it's going to have that value in there. Okay. And then to calculate, so that's basically my lower bound. If I were to set up my integral here, it'd be from here to here. So to calculate that one, it does end up being at 1. But we can use this quick. Calculate intersection point. So now it's on my, oh shit, red curve. Toggle, 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 get close. First curve, second curve. Okay, those intersect at -1, 1. Nice, easy, clean point. Okay, so let's just kind of quick sketch what we're doing on our graph really quick. We might run out of time, but that's okay. So I have my cubic curve that looks something like this. And then I have this sideways parabola here. It does not have to be that accurate, something like this. And we're finding this region. And as we said before, we're going to do this with respect to y using horizontal rectangles. Okay, so what you can do is you can label these intersection points. You can label this one as 1, and let's label this one as B, what we stored in B. If you want to put the value, you can. Approximately -1.4367. So we calculated the intersections, and then we stored B as that 1, and then the other one just ended up being 1. Okay, now we can set up our integral. So we would do from B, and you can put that right in your integral because that's what we're going to type in our calculator. From B to 1, we're going to do right minus left. So the red curve, which I'm going to have to put in terms of y, divide cube root. So -y to the 1/3. Oh, rats. Okay, we'll finish this tomorrow. I will save this spot exactly. This was important. I don't want to rush through it. How to do that on your calculator.